Good morning. This is lecture of physics for mechanical 2. In this lecture, we have to discuss some important questions. And the first question is, explain equation of continuity for time-varying field. Equation of continuity simply represents the conservation of the charge also. Equation of time-varying field in the static equation of continuity we can also explain in the static field also, but in time-varying field equation of continuity represents the law of conservation of the charge, that is the charge flowing out through a closed surface in the some volume is equal to the rate of decrease of the charge within the volume. Means the charge inside the closed surface is equal to the charge that is flowing out the surface is equal. This is known as equation of continuity. So what is the statement of this theorem, equation of continuity? Equation of continuity represents the law of conservation of the charge, that is the charge flowing out through a closed surface in some volume is equal to the rate of decrease of the charge within the volume. Now we have to prove this theorem, that is the conservation of the charge, and for that we have to write the formula of the current, because current deals with the charge. So here first of all current is equal to charge per unit time. Here small amount of the charge dq divided by small amount of the time dt. Small amount of the charge is flowing out through the surface in the small time dt. Here negative sign shows that the charge is flowing out or rate of decrease of the charge within the volume, where I is the current flowing out through a closed surface in a volume, minus dq upon dt is equal to rate of decrease of the charge within the volume. Now because the statement of the theorem is related to the conservation of the charge, so we need the charge densities and the current densities, where J is a conductor current density, rho is a volume charge density, and as we know current density is equal to current per unit area. So small amount of current di upon ds is equal to J. From this we need di. Di is equal to J vector dot ds vector, and the total current we can find out by doing integration of this vector. So I is equal to closed integral in surface integration of J vector dot ds vector. Now next is, this is current density, we need volume charge density, which is equal to dq upon dv, and from here dq is equal to rho into dv and q is equal to triple integration of rho into dv. Now see the expression first, I is equal to minus dq upon dt. Here we get the value of I and the q also. So simply what we have to do now, fill the value of I and the q in the equation number 1. So after putting the value, closed integration of J vector dot ds vector is equal to minus integration of curl rho upon curl t into dv. Now applying the Gauss divergence theorem on the left hand side. Gauss divergence theorem simply converts the surface integral into the volume integral. Here this is a surface integral, so this will become del dot j into dv is equal to minus, this is also volume integral, curl rho upon curl t is into dv. Now volume integral cancel out with volume integral, so we are left only with del dot j is equal to minus curl rho upon curl t. So del dot j is equal to minus curl rho upon curl t. Now bring this factor towards the left hand side, we get del dot j plus curl rho upon curl t is equal to 0. This equation is known as equation of continuity. This is the charge inside the surface and this is a charge flowing out the surface. So simply equation of continuity shows the conservation of the charge only. this is the equation of continuity for the steady time varying field. For the steady current means J curl rho upon curl T is equal to 0. If curl rho upon curl T is equal to 0, then above equation become del dot J is equal to 0, and this is the equation of continuity for the static field. Now the next question is Maxwell's equation. As we all know, here are 4 Maxwell's equation. And the first Maxwell equation is del cross E is equal to minus curl V upon curl T. Second Maxwell equation is del dot E is equal to rho over epsilon naught. Third is del dot J is equal to 0. And fourth is del cross H is equal to J. Here all the above 3 equations are correct for the time varying field. Fourth equation is not good for the time varying field. So we have to need to modify it. So from equation number 4, take divergence both sides. After taking divergence is simply multiply the del with the vector quantity. So after taking divergence, we get del dot del cross H is equal to del dot J, and from the previous value which we have find from the equation of continuity for the steady current, del dot J is equal to 0. And for the conservative system means conservative charge, del dot J plus curl rho upon curl T is equal to 0. So this is equation number 5 and this is equation number 6. Simply we have to compare these two equations. So after comparing these two equations, we get del dot del cross H is equal to del dot J plus curl rho upon curl T. Now simply we have here fill the value of rho. Rho is a volume charge density. And from first Maxwell's equation, second Maxwell's equation, that is del dot E is equal to rho upon epsilon naught and D is equal to epsilon naught E. So from here E is equal to D over epsilon naught and rho is equal to del dot D. Simple. So fill the value of the rho here. After filling the value, we get del dot del cross H is equal to del dot J plus curl by curl T del dot D. Now takes del as common from these two factors. We get del dot J vector plus curl D upon curl T is equal to del dot del cross H. So simply del cancel with del. We are left only with del cross H is equal to J vector plus curl D upon curl T. This is called modified Ampere circuital law. And this is fourth equation of Maxwell's. So fourth equation of Maxwell is del dot D is equal to rho, del cross E is equal to minus curl V upon curl T, del dot A is equal to 0 and del cross H is equal to J vector plus curl D upon curl T. So these are the 4 equations and we have modified the fourth equation, that is Ampere circuital law. Now the next question is explain the fundamental postulates of magnetostatics. Magnetostatic is based upon 2 postulates. In magnetostatic we have 2 fundamental postulates, and for that we have to consider an infinite long wire from minus infinity to positive infinity carrying current from cross-section point of view. When we take any object from the cross-sectional view, then that thing appear us as a point. So this thing will appear us as point. So here this point is an infinite long wire and the circle around this represents the direction of magnetic field lines. So the magnetic field, this is the wire, this is point P, and the distance between point of wire and the point of observation is R, and the path is C1. Then the magnetic field due to infinite straight wire at point P is B is equal to mu naught I upon 2 pi R. Line, so now the line integral of the B around the closed path C1, B vector dot dl vector line integral is equal to, and as we know P is equal to magnetic field at the point P is equal to mu naught I upon 2 pi r into dl. So here we simply fill the value of P. So after filling the value, we get B vector dot dl vector is equal to mu naught I upon 2 pi r, because mu naught I upon 2 pi r, these parameters are constant. So we are left only with dl. dl is a small length element and we have to find out the total length, that is circumference of the circle, which is equal to 2 pi r. So B vector dot dl vector is equal to mu naught I upon 2 pi r into 2 pi r. 2 pi r cancel out. So we are left only with mu naught I, and this is called Ampere's circuital law. So the line integral of magnetic field is equal to the time current enclosed by the closed contour or the closed path. Now applying the Stokes theorem on the above equation, left hand side, Stokes theorem simply converts the line integral into the surface integral. So after applying the Stokes theorem here, we get del cross B dot ds surface integral is equal to mu naught I. Now J is equal to di upon ds, and from here di is equal to J dot ds, and total current is equal to surface integral of J vector dot ds vector. So here this equation will become this and this equation become this. So after filling the value of I in the above equation, here we get del cross B dot ds is equal to mu naught surface integral J vector dot ds vector. So surface integral cancel out with surface integral and ds cancel out with ds. So we are left only with del cross B is equal to mu naught J vector. This is differential form of Ampere's circuital law, and the integral form is B vector dot dl vector in line integral is equal to mu naught I. This is integral form of Ampere's circuital law, and this is the first postulates of Ampere's magnetostatic. Now for the second postulate, that is which is equal to del dot B is equal to 0, we have to simply write the expression of magnetic field due to the volume current density, and which is equal to mu naught upon 4 pi volume integral J vector cross R vector minus R dash vector upon R vector minus R dash vector mod whole cube into D dot dash, where D dot dash is a volume and V having component of x, y, z, J dash having component x dash, y dash and z dash, D dot dash having component of x dash, y dash and z dash, R vector minus R dash vector is equal to R, which having component of x, y, z, minus R dash, which having component x dash, y dash, z dash is equal to R vector. Now fill these value in the above equation, we get B vector mu naught upon 4 pi J vector cross R vector upon R cube into D dot dash. Now take divergence on both sides. We get del dot B is equal to mu naught upon 4 pi triple integration del dot J vector cross R vector upon R cube into D dot dash. So after taking the divergence, we have to apply identity here. And the simple identity is del dot A cross B is equal to B dot del cross A minus A dot del cross A. Here we have simply replaced the A vector with the J and B vector with R vector upon R cube. So after filling the value of A and B here, we get J vector cross R vector upon R cube is equal to R vector upon R cube del dot J del cross J minus J vector del cross R upon R vector. As we know, del cross R vector upon R cube is equal to 0. Similarly, del cross J is equal to 0 because J having component of x dash, y dash and z dash, and del having component of x, y and z. So we will get del dot J vector cross R vector upon R cube is equal to 0. So here in the above equation, that is in this, del dot J vector cross R vector upon R cube, the value of this is equal to 0. So after substituting this value, we get 0, means del dot B is equal to 0. and this is known as differential form of the second postulate of magnetostatic. And the integral form is p vector dot ds vector is equal to 0 around a closed surface integral. So the two postulate in first postulate is simple, del cross b is equal to mu naught j vector, and the second postulate is simply b vector dot ds vector is equal to 0. So in this lecture we have discussed three important questions. First is equation of continuity for the time varying field, and the second one is Maxwell's fourth equation, and the third one is postulates of magnetostatic. Hope you will understand. Thank you.